Hey guys, and welcome back. This is our third episode of Quantum Chemistry Lectures. Again, I apologize that I couldn't be present in person to talk about these exciting topics, but I think when it comes to the spin and relationship of spin with magnetism is a topic we'll be discussing a bit more as we go to multi-electron atoms, so I'll still be able to touch upon some of these concepts on Friday and then on the week that follows. Okay, so the spin is really quantum phenomenon. Okay, so this is something that we haven't seen before, right? We've seen all kinds of weird concepts, weird quantum mechanical behaviors like the quantization, the probabilistic behavior of the electron, but spin is going to surprise and shock us in ways that all these other quantities haven't done. Okay, and so we have quite a bit of an agenda here. We're going to discuss the relationship of spin with magnetism. We're going to introduce, magnetism from the classical mechanics point of view. Then we're going to look into this classic experiment, Stern-Herlach experiment that uncovered the spin for the first time and the confusion that resulted in quantum mechanics. Then we're going to acknowledge that spin is as fundamental as mass or charge, and it applies to all the subatomic particles. And that's going to lead us to a Pauli exclusion principle that is crucial for understanding the behavior of the electrons in atoms. And then we'll finish by discussing a couple of interesting effects that complicate the interpretation of electronic spectra of atoms. Okay. All right, so this is quite a bit of an agenda, so I'll try to pack this into one lecture. We'll see how it goes. Okay, so first we want to discuss the magnetism, okay, the magnetic fields, and we start with acknowledging that if you have circulating charge, right, if you have a charge objects that are moving in circles, they're going to generate magnetic fields. Okay, so this is basically meaning that you're generating a force that can disturb magnets around. Okay, so here is the a little animation that shows that. So whenever you close that little thingy and allow charge to circulate, it's going to apply force to the compass or the magnet that's nearby. Okay, so this is the meaning of a magnetic field. You can think of it as force acting throughout the three-dimensional space. Okay, so this is something that's been well known in classical physics, and people have done some amazing experiments developing magnets and using electricity to generate magnetic fields. Now, what's the essential physics here, right? So the charge that is undergoing a circular motion, right? We know that it's characterized by angular momentum L, right? So this is what this figure 80 is showing. Right, and if the particle is charged, it's going to also generate a magnetic moment. Okay, so this is what allows to interact with magnetic fields, or generate a magnetic field. Right, so basically, if you have a charge that's doing a circular motion, you are going to attach a magnetic moment to it, and this is going to describe its interaction with magnetic fields. Okay, so this is a source of magnetism. So mathematically, and here let me actually switch to my notability so I can draw some stuff here. Right, so here we see that a simple relationship between a angular momentum, right, and the magnetic moment. Okay, and there is just a prefactor that's called a gyromagnetic ratio, or magnetogyric ratio, or whatever, the same meaning. Okay, and it consists of fundamental constants, charge of the electron divided 2 times mass of the electron. So basically a simple relationship. If you have a rotating charge, it's going to generate a magnetic moment, and this magnetic moment is going to interact with magnetic fields. Okay, so that's good. You can see that just like L is a vector quantity, so is mu, the magnetic moment. And oftentimes, to simplify things, we're going to look at one particular axis, the axis z, and we can then deal with scalar objects. So mu z is related to Lz the same way. And in quantum mechanics, right, we know that LZ only takes particular eigenvalues, right? And it's, if you remember, the eigenvalues for this guy was h bar m, right? So those were the eigenvalues of the LZ operator. Okay, so essentially, from the classical mechanics, we can smoothly transition to quantum mechanics and predict that, you know, if LZ is quantized, so is going to be mu z. Okay, so mu z is going to be quantized the same way, and just the prefactor is going to be different. And this prefactor, which absorbs a whole bunch of fundamental constants here, the mu b, right, this guy is called a Bohr magneton. Okay, so far things are pretty straightforward. You have a charge that's doing circular motion, has an angular momentum, it results in magnetic moment, okay? And this magnetic moment then can interact with magnetic fields, okay? In other words, it's a source of magnetism. And the interaction energy between two vector objects is described by a scalar product, dot product, between a magnetic moment and some external magnetic field, okay? And if you take a dot product of these two vectors, it's going to give you a scalar, all right, which is the energy of interactions, okay? And this is from linear algebra, right? Dot product of vectors is the product of magnitudes times the cosine angle. Okay, so if these fields are perfectly aligned, the interaction is going to be strong. And if they are perpendicular, it is going to be no interaction. In other words, if you have some magnet in a magnetic field, right, this magnetic field is going to apply a force or a torque that is going to try and align it along the B, okay? So it's going to try to align this magnet along this direction, because that minimizes the energy. You see there is a negative sign here, right? So magnetic field is trying to orient the magnets in a way that minimizes the energy of interaction, okay? So these are concepts that, you know, come from classical mechanics, and all we have to do in quantum mechanics is simply replace the angular momentum by its eigenvalues, right? So this is the standard recipe of quantum mechanics, and we got the interaction energy of magnetic moment with external field. And for LZ, we can plug in whatever eigenvalues correspond to the value of L, right? So we know that we have two quantum numbers, L and ML, and ML goes from minus L dot 0 dot L, right? So, and we can easily plug in those values and get the interaction energies. Okay, so far so good, right? When it comes to electrons, we know that they can have non-zero angular momentum, right? Hydrogen atom, we discussed that it's characterized by N, L, ML quantum numbers, and L goes from 0, 1, dot dot dot. Oh, no, I mean, it is going to be bound by N, but in principle it can go all the way. So basically, from here we can already make some predictions. If the electron is in an orbital, or if it's characterized by wave function 1s, or any wave function that's L is equal 0, then we expect to have no magnetic effects, right? Because L is 0, ML is 0, and if you look at this equation, right, you'd see that you just have to plug in h bar times ml, so this is going to give you zero interaction energy with zero magnetism. Okay, so this is nice prediction. So we can tell for sure that you need to be in an orbital such as 2p, right, or 3d, right, orbitals that are characterized by L not equal to 0. Okay, so this is crucial. So if you're in a 2p orbital, then sure, you can generate a magnetic moment, and you can apply external magnetic field, and the external magnetic field is going to interact with this a magnetic moments. Okay, so here are the eigenvalues for the LZ operator acting on p plus 1, p0, p minus 1. You can see that they are non-zero, so you're going to have some magnetic moment. All right, this is fine. That means that if you're in a 2p orbital, then your atoms would be affected by external magnetic field, which is shown here. So if you put the hydrogen atom in an excited 2p orbital, right, then they are going to be oriented by the magnetic field. Okay, so they're going to apply forces to these hydrogen atoms, and they're all going to line up nicely. Okay, and then here clearly, right, you're kind of seeing the connection between angular momentum, magnetic moment, and its interaction with external magnetic field. Okay, so far so good. This is the part where classical mechanics once again works nicely with quantum mechanics. All we have to do is replace the classical quantities with quantum mechanical operators. The only difference being that quantum mechanical observables, right, they only take discrete values, the eigenvalues, and nothing else. Okay, that's the difference, and everything else works. Okay, so that being said, right, now we can have a recipe for extending our Hamiltonian if we have an external magnetic field, right? So this is the hydrogen atom in the absence of magnetic field, and if you do have an external magnetic field, B not equal to 0, then it's going to add one more term that describes the overall energy of the system in interaction with the external magnetic field. And that's it. Okay, so basically you have your hydrogen atom Hamiltonian plus the term that accounts for the interactions with external magnetic field. And if you're in a 2p 3d orbitals, L is not equal to 0, so you definitely expect to get some effect. Okay, and this this begins to shed some light on why we call this quantum number ML, right, the magnetic quantum number. You can see that it directly goes into the expression for interaction with the magnetic field. Okay, so this guy, now we can appreciate why it's called a magnetic quantum number, because it describes interaction with external magnetic fields. Okay, so here we're once again showing the important eigenvalues that we need to plug in and get the energy of a hydrogen atom in a magnetic field. Right, we know that it's both operators of Hamiltonian and LZ. They commute, first of all, right, and therefore unsurprisingly they share the same set of eigenfunctions, and they just have a different eigenvalues. Okay, now all we have to do is take these eigenvalues, plug it into the expression, and we have the energy of hydrogen atom in an external magnetic field. The magnetic field is not equal to 0, so it can have strong magnetic field, weak magnetic field, etc. And the key quantity here is the ML, a magnetic quantum number that's going to describe the different energy levels of the hydrogen atom. Okay, so here let's pause a little bit and see what's going to happen to 2p orbital, right? 2px, 2py, 2pz, or physicist notation could be 2p minus 1, 2p0, 2p, it's a 2p, what is it? Plus 1, 0, minus 1, right? So basically, what we see here, that in the absence of magnetic fields, we discovered there's a huge degeneracy, right? There's only n that determined the energies, right? Only this number. But when you do have the magnetic field, what's going to happen is that suddenly some of these levels are going to go lower in energy, and others going to get high. Okay, in particular here you see the ML, right? If it's a negative, this guy is going to go down. If it's positive, it's going to go up, and if it's 0, it's going to stay the same. Okay, let me draw somewhere else what's going to happen, right? So you had 3 lines, and now they are going to split, and you're gonna get -1, 0, +1. Okay, so the 3 orbitals that had the same energy in the absence of magnetic field, once you put it under the influence of external magnetic field, it's going to interact differently with different orbitals characterized by different magnetic quantum number, and it's going to then end up giving different energies. Okay, so you're going to have lower energy, higher energy, and the highest energy. Okay, and it's going to also apply the same way to all other orbitals that are characterized by L not equal to 0. And this effect of splitting of energy levels in the presence of magnetic field is called Zeeman effect. Okay, so this is This is something that people observed early on when they would detect spectra of hydrogen and other atoms in the presence of magnetic fields, and they would see more lines, right? So they will see the more complicated spectra. And these addition of the magnetic field into the energies completely describes the spectra. Okay, so you have your energy in the absence of magnetic field, and here you have the energy in the presence of magnetic field. And here is the here's the nature of electronic transitions. You see, if you have no magnetic field, it's pretty simple. You just have 2p 1s transition. But if you have a magnetic field, then you can have different kinds of transition. You can go from 2p plus 1 to 1s, 2p0 to 1s, 2p minus 1 1s, and they're all going to correspond to different photon frequency, h nu 0, h nu minus 1. Okay, so Zeeman effect is experimentally well described by these formulas we just wrote down, right? And it leads to complicated electronic spectra of atoms. Okay, so far things are relatively straightforward, right? Straightforward extension of quantum mechanics machinery, right? You have an external field, fine. You're adding one more piece of the piece to the Hamiltonian, right? Described by the interaction of the magnetic field, and you solve the problem, and you discover that energy levels are different, and they're described by magnetic quantum number ml. Okay, so you went from the dependence only on n to dependence on n and ml. Fine. Now let's see something a bit more exotic and appreciate why this discovery of quantum mechanical spin really shocked the world of quantum mechanics. Okay, and for that. Let's actually watch a little video here. We're gonna watch a video of a video. How cool is that?
The physical explanation turned out to be electron spin. Electrons have an intrinsic property that is best observed with a modern version of the Stern-Gerlach experiment that used silver atoms. Here we use magnets and electrons directly. The device has a north and south pole shaped to create a magnetic field that is stronger near the tip. This varies the force on charged particles passing through. A magnet is sent through with the north pole up and the south pole down. The magnetic field creates a force that deflects the magnet upward as it passes through the field. As we change the orientation of the magnets being sent through, we see the change in the amount and direction of the deflections. The deflections depend on the orientation. This is as expected. When electrons are sent through the field, they too are deflected. But they always arrive at the screen deflected either up or down, never in between like the magnets. Each electron behaves as a magnet, but with only one of two possible orientations, up or down. This intrinsic property of an electron is called spin. It is interesting to note that whenever an electron in an atom changes state, the atom's angular momentum changes. For example, here an electron moves from a higher energy orbital with angular momentum to a lower orbital with no angular momentum. We see that the emitted photon carries away both the energy and the angular momentum, giving it a spin equal to 1. With the Pauli exclusion principle and spin as the fourth quantum number, the full set of spectral lines, orbitals, and geometries and interactions with each other fell into place. In fact, when we add this fourth quantum number to Schrödinger's equations, we can generate the entire periodic table of the elements.
All right, so this was a pretty good video, right? It gives you a little bit of a teaser of what spin, the concept of spin does for the chemistry, for the quantum mechanics, and how it really shakes the world. So let me also pause here a little bit and discuss this Stern-Herlock experiment. Find a little space here. So essentially, what the experiment found is that even if you're even if you have an electron or an atom in an s orbital, right? Let's say you have a hydrogen atom, let's say in 1s orbital, or some other atom that is described by external 1s, right? And you have L equal 0. You still see the interaction of this electron or atom with the magnetic field. Okay, that just shows that there is something more than the classical source of magnetism in atoms and electrons. Okay, there is more than what can be described by the angular momentum. And the funny thing about this is that there is no classical analog. Okay, the spin is purely quantum mechanical, and there is nothing more fundamental to derive the spin from, right? So basically, the way we acknowledge the mass, the charge of the electron, we just have to come to terms that these subatomic particles are also characterized by spin values. For the electron, we're going to write spin is equal 1/2. We'll see there are other particles for which spin could be integer number 1, or spin is equal 0, right? So basically, we're coming to terms with a fundamental reality of subatomic particles, that each of these, protons, neutrons, photons, electrons, they each have a spin, and it's in their very fabric. Okay, so this is to contrast with the classical source of magnetism, where you have a rotating charge that generates a magnetic moment, right? And has a classical analog. You can replace a classical observable with a quantum mechanical expression. No such things for spin. Okay, spin is just there. It's just the nature of the subatomic particles. All right, so understanding spin is not going to be as easy, and in fact, I don't know if we can even apply the word understanding here. It's more like, we have to come to terms. We have to acknowledge that there is mass, there is charge, and there is a spin. Fine. Okay, so the experiment clearly demonstrated that electron is characterized by two possible values, and here you can write down ms is plus 1/2, ms is equal minus 1/2. So here we're emphasizing the analogy with the angular momentum, right? So the ml could go from minus L, dot, 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 0, dot, 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 L. For the spin, we're just discovering there are only two possible values, minus 1/2, plus 1/2, okay? And therefore, S is 1/2. Okay, so this is something discovered from the experiments, and we're simply writing down the possible values. Now, having worked through a number of quantum mechanics problems, we can say that we have two eigenvalues, right, for the projection of a spin, and we're talking about some z orientation of this magnetic field, right? So we can say that there are only two eigenvalues for this operator of the spin, and there is only one eigenvalue for the total spin operator. Okay, so we're going to talk about a z operator and s operator, and we can already see that one guy has two eigenvalues, 1, 2, and the other one has only 1. Okay, so we can simply write down the eigenfunctions and eigenvalues from the experiments. Okay, so this is the direction that we're going to go, sort of work back from the experiments to build spin into quantum mechanics. Now, I guess the question that is popping up in your mind is that how could we have missed the spin, right? Didn't we acknowledge, or didn't we account for everything that's possible, all the interactions, all the terms? Yes, we did. And the key problem, right, or the reason we missed the spin is that it had no classical analog, right? So the recipe we used is to take the classical Hamiltonian with kinetic energy, potential energy, and just put hats on them, right? Just turn them into operators, and it worked fine so far. But the spin is such a quantity that has no analog in classical mechanics, so it has to come from somewhere else. and that somewhere else is the theory of relativity. And in fact, Dirac has shown that if you account for theory of relativity, you end up with a slightly different version of the Schrodinger equation that's known as Dirac equation, which is less sort of widely, I guess, useful in quantum chemistry, electron structure calculation. But this equation then fully, describes the spins, and naturally sort of spin is accounted. Okay, so we can see here that the roots of the spin go much deeper into the fabric of subatomic particles, into relativity theory. But the good news is that once you acknowledge the spin, you can easily add it into your picture of wave functions and the Schrodinger equation. Okay, all you have to do is acknowledge that electrons, protons, all these objects, they have spin, and spin has corresponding operators, eigenfunctions, and eigenvalues, and that's it. Okay, so you can build into Schrodinger equation with no problems. And for all the calculations, all the discussions, we're going to use Schrodinger equation. We don't have to talk about Dirac equation, which is essentially a Schrodinger equation with sort of relativistic with terms that account for relativistic effects. Okay, so let's see how the spin, once we discover and acknowledge how it can be built into the familiar now quantum mechanical machinery. So we just discovered that there is only one eigenvalue for the spin. It's 1/2, and it has two projections, up and down, or plus minus 1/2, right, in an external magnetic field, z direction. The atoms, they orient in only two possible, and they only display two possible orientations, plus 1/2 and minus 1/2 values, right? And you can measure, this, on the screen. You can calculate the eigenvalues experimentally. And so we can write down these eigenvalues explicitly using the analogy with the angular momentum, right? If you remember, the eigenvalues for the angular momentum were h squared L plus 1. So here the analogy is direct. You have s times s plus 1 h bar squared, with the only difference is that s only has one fixed value with only two possible projections. Okay, so in that sense, there's quite a bit of similarity between L and S, and LZ and SZ. After all, they're both source of magnetism, right? The difference being that this guy is coming from sort of the rotational type of motion, right? Circulating charge. And this guy is coming from very deep, from the very fabric of subatomic particles. So you can say that this is intrinsic source of magnetism, and this is extrinsic or external. Is there such a word, extrinsic? I don't know, I'm confusing myself. Oh, no, external. Okay, so this is sort of coming from the circular motion of the charges, and the other one is coming from the very nature of the particles. But other than that, we can see that they share a lot of the similar relationships. Okay, they're both generating sort of the magnetism in atoms and molecules. Okay, so let's complete this picture of eigenfunctions, eigenvalues, right? So here we're going to write down the eigenfunctions of the spin, right? So far we wrote down their possible values, which were 1/2 or plus minus 1/2 for the projection. So the eigenfunctions of the spin are going to be called alpha and beta. Okay, so unlike the other kinds of eigenfunctions that we've seen so far, right? Sort of the hydrogen atom, something like this, right? Sort of the positional dependence. The spin eigenfunctions are pretty dumb. I mean, there are only two of them, and that's it, because there's only two eigenvalues. Okay, and we can label them as alpha, beta, or in chemistry we like to call them spin up, spin down, right? And we also draw them with pointy arrows. Arrow goes up, arrow goes down. So they basically refer to these eigenfunctions of the spin, alpha, beta, whichever way you want to write it. Okay, sometimes we'll write it explicitly that this is an eigenfunction of spin, and the S can take a value of 1/2 for the electron, and for other subatomic particles it can be different values. Okay, so here is a full picture of eigenfunction and eigenvalues for spin. Nothing surprising here. This is the projection, right? Notice there's a z, and this is the full value of s. Similar type of relationships as we had for angular momentum. Okay, so let's see how their operators interact. All these operators are commuting, which is great. That means that they share the same pool of eigenfunctions, right? So we wrote down the hydrogen atom eigenfunction with N, L, M, L, and now we can add one more quantum number to fully describe the electron. Okay, now we have 4 quantum numbers: the principal angular momentum, projection of angular momentum, and ms, which can take values of +1/2 or -1/2, or in Dirac notation it will be NL, ML, ms. Okay, so for instance, let's write down the 1s orbital. 1s orbital would be 1 here, 0 there, 0 there, and this guy is, let's say, +1/2. Okay, and you can write down the 2p orbital in a similar way, right? And a 2p orbital would be 1. This guy has to be, not 1, has to be 2 now. 2, right? The principal quantum number, L is equal 1. So ML can take 3 possible values, so why don't we just pick 1? Let's just pick -1 for this guy, and for the spin, let's pick -1/2. Okay, so there's a number of values that are possible for ML and MS. Okay, we'll be seeing these eigenfunctions quite a bit more in the multi-electron systems. For the hydrogen atom is quite simple. So the similar type of relationship between eigenfunctions apply for spin eigenfunctions. They're orthogonal, alpha alpha, and orthogonal and normalized alpha alpha beta beta dot product should give you 1, and alpha beta beta alpha should give you 0. This will be really important once we write down multi-electron wave functions and I try to describe the energies in multi-electron atoms. Okay, so this orthogonality is going to simplify a huge number of expressions. Okay, so these eigenfunctions of the spin may sound a bit mysterious to you, and that's okay, because unlike the other eigenfunctions that depended on the position, spin eigenfunctions they're a little bit different objects. In fact, they're much more simpler, and you can probably imagine what they would be like, right? So essentially, just to give you a little bit of a sneak peek into the world of spin operators and their eigenfunctions. So these operators and eigenfunctions are described by 2x2 matrices and 2-dimensional vectors, okay? Just like that, because spin is a 2-dimensional object. It's either +1/2 or -1/2. Okay, and these operators of spin in quantum mechanics, they're called Pauli matrices. They look like this, and here is your alpha and beta. Here is how they look like. And you can clearly see that these guys would be orthogonal, right? Because if you take a dot product of 1, 0 with a 0, 1, it's going to give you 1 times 0 plus 0 times 1. It's going to give you 0. Okay, so they're fairly simple objects, much simpler than the other eigenfunctions of positional operators like Hamiltonian, angular momentum that have complicated R and theta phi dependence. So, and you can clearly see how they act on how the spin operators act on their eigenfunctions, or in this case they are kind of 2-dimensional. It's an eigenvector. Okay, so this is an operator here, and this is the eigenvector eigenfunction. You do matrix vector multiplication, and you end up with the result that we just highlighted before. Okay, and a similar way for action on a beta eigenfunction. Okay, so we're not going to use this. It's just to show you how simple these spin operators and their eigenfunctions, eigenvalues look like. They're going to be easy to build into the main wave functions. And that's the recipe we're going to use. We're going to attach one more factor to our wave function, right? That will depend on r, theta, phi, and then we're going to add either alpha or beta, right? This is the spin part of the wave function, and everything else is gonna proceed the same way. All right, now we're back to describing the interaction with magnetic field, and here the picture is going to be very similar to the magnetic moments that were generated by angular momentum. Okay, so in this case, the magnetism comes from the intrinsic internal nature of the electron. You see the relationship is almost the same. So before we had L generating the magnetic moment, right, due to L, and there was a prefactor, and here we also have a similar relationship. The only difference is that there is this prefactor that's called a G factor, and it comes from much deeper place, from electrodynamics. We're not gonna delve too deep into that. So there's this factor that needs to be thrown in there, but other than that, the relationship is the same. Okay, there's a constant of proportionality, there is a minus sign, and you have a relationship between a spin operator and the magnetic moment. Okay, so we have one more source of the magnetism. And the same way that we did for the angular momentum, projection of angular momentum, for the projection of the spin, we have this a quantum number that goes +1/2 or -1/2, and now if your electron has a spin, of your atom, multi-electron atom, has a total net spin that's different from the zero, then as someone who knows quantum mechanics, you're going to expect interaction with the magnetic field, and indeed that's what you're going to see. Okay, and you can calculate the energy the same way as a dot product, of the external magnetic field with this spin operator. So what do we have? We have one more term that we're going to add to the Hamiltonian. Okay, so this is the Hamiltonian for the hydrogen atom in the absence of the magnetic field. This guy is due to the electron being in one of the orbitals that's described by a non-zero angular momentum. So basically you have some kind of a rotational motion, not to be confused with any sort of Bohr orbit or that kind of nonsense. Right, it has to do with the some kind of rotational motion of a probability distribution, so quantum mechanical rotational motion. Okay, and then you have this source that we just discovered, right? There's a spin, we just have to deal with it, you have to acknowledge it, that's how nature works. And we have this sort of more permanent source of magnetism. If you have an electron 1/2 or a multi-electron atom which has a net spin of 1/2, or non-zero, then you're going to see another source of magnetism. Okay, and so if you add them together, you have your new shiny Hamiltonian, and you can plug in those eigenvalues and see the kind of energies that you get. Okay, so now your energy in the external magnetic field could potentially depend on three quantum numbers, n, ml, and ms. Okay, so you have three contributions, and this is going to lead to more complicated splitting of energies. Okay, so this brings us to the final part of this lecture, and it's going to tell us something crazy, right? Is that you have two sources of magnetism inside the atom. So you may wonder, can these two magnets inside the atom interact with one another? And the answer is yes, and that's what you see. Okay, so electron, right, can have a magnetic source of magnetism due to angular momentum, and it can have a source of magnetism due to the spin. And so you can think of it as two tiny magnets coexisting inside the atom. Even the simplest atom, like hydrogen atom with a single electron, it generates two sources of magnetism, or two magnetic moments. And these two tiny magnets can interact with one another and perturb, right, the energetic levels. This is crazy, but this is what's being observed. Okay, and this phenomena is known as spin-orbit coupling, and it's acknowledging the fact that L and S interact with one another, and this is going to require another term in a Hamiltonian if you want to account for this fact. Now notice that unlike the effect of the strong external magnetic field, this effect is much weaker. Okay, so there is the R3 dependence here, so it just shows you that this is a much more fine effect, and in fact this is only observed. This spin orbit coupling can affect the spectra of the atoms if you don't have any strong external magnetic field that can dominate the energy levels, right? You can only have this effect pronounced when you have some sort of weak magnetic field, right, or the absence of magnetic field. Only then this term would be important. Okay, the spin-orbit coupling. Okay, so the 1 over r cube, this I guess also can answer the question one of you asked, like why we need to calculate this kind of averages of 1 square, 1 over r, 1 r that we did for hydrogen atom, because you're going to see these different kinds of contributions in a Hamiltonian where we'll need to compute the averages of 1 over r square or 1 over r cube. Okay, so what does this spin-orbit coupling do to our quantum numbers? Turns out that if you introduce the spin-orbit coupling into the Hamiltonian term, all of a sudden L and S stop commuting with the Hamiltonian. Okay, what does it mean? You can say, oh, what's the big deal? They don't commute, they don't commute. Well, if they don't commute, that means they don't share the same pool of eigenfunctions, right? So that means that we have to come up with another quantum number that will commute with the Hamiltonian, right? And the values of this new quantum number can then describe the eigenfunctions. I know, sounds a bit complicated, it's quantum mechanics, but it follows the same principle, right? So we could use all these quantum numbers, right? N, L, ML, and MS in the absence of spin-orbit coupling, because the corresponding operators would all commute together, right? That means they could all share the same eigenfunction that would write down like this. Okay, so this is in a world where we don't have spin-orbit coupling. If we do have the spin-orbit coupling, these L and S interact with one another. They are coupled. So we have to then acknowledge the fact that there is a total angular momentum, which consists of the sum of, oh, there is a mistake here. This guy should be equal, J is equal L plus S. Okay, so the total angular momentum that is going to describe the overall sort of the magnetic moment inside the atom. So this part, is a little bit subtle, right? So you have these two magnetic moments, or two angular and spin momentum, and you now have to combine them to get a new angular momentum, J. But the good news is that L is quantum following a straightforward eigenvalues, and spin is quantized. They're both vectorial quantities. So this J object, right, which is the sum of L and S, is going to be quantized the same way. And since L and S are vectorial quantities, their eigenvalues are going to follow the same type of quantization. They're going to be different by integer values. And MJ, just like L and S, right, the projection is going to run from minus J dot 0 dot J, so it's going to be 2J plus 1 values for the projection, just like we had 2L plus 1 and 2S plus 1 values for the spin. Okay, so this is what this picture is showing you, right? Showing you that you have S component and L component, and they sum together to give you the J. And then, the L and S being vectorial quantities, right? Spin being either up or down, right, is going to add up to L in a very predictable ways and give you the eigenvalues of J and MJ that can be computed from L and S. So in other words, is that yes, it complicates this spin-orbit coupling complicates the picture a little bit, but if we understand L and S, we can put them together and end up with the values of J that can describe the effect of spin-orbit coupling. Okay, so let's go over a couple examples here. Here we're writing it with explicitly acknowledging the vectorial nature of L and S. So this is just sort of a schematic equation. Don't think about it in a classical mechanical sense. Just saying that these guys are vectorial. They have X, Y, and Z component. Now, for the hydrogen atom, life is simple. There's only one electron. S is equal 1/2. That's great. The L can run from 0, 1, 2 all the way to n minus 1. Okay, so we just have to watch which orbital the electron is occupying, and from there we can calculate the possible J values. Okay. So angular momentum is quantized because it's a sum of two quantized quantities, and the eigenvalues are going to run from L minus L all the way to L plus L, because this is the only way to add up, spins up and spin down, right? And you know, this is the only way that you can quantize this quantity. In fact, all these eigenvalues also emerge when you explicitly write down the J operator and, you know, act on the psi, and you get J plus 1. So you can, you know, you get this from rigorous mathematics, but here it's also easy to construct from the already obtained eigenvalues. Anyway, so these are some easy ways of extracting J values, the total angular momentum, if you know L and S. Okay, it's going to run from L minus S, L plus S. For the hydrogen atom, it's extremely simple. For the multi-electron atoms, we'll discuss a little bit more. So let's see how things work out for the hydrogen atom. Since S is fixed, let's see what kind of J values we can have. If L is equal 0, right, so the only thing we can do is, you know, is get the value of 1/2, okay, because J can run between L minus S, right, to L plus S, and since S is equal 0, we end up with a single possible value, 1/2. Okay, so J is 1/2, right, and the projections of the MJ, right, they take 2J plus 1 values. Okay, so in this case, going to be 2 times 1/2 plus 2. So there's only 2 possible values of J total angular momentum. All right, so if L is equal 1, we can see that we can add this sort of a spin eigenvalue in 2 different ways, right? So again, we're running from L minus S to all the way to L plus S with increments of 1. So we get 1/2 and 3/2. Okay, those are 2 possible values of total angular momentum, and you can continue this procedure, right, and see that, you know, if your L is equal 2, you can either subtract or add the spin, right, so you end up with 3/2 and 5/2 as the possible values. And you can generalize it for the hydrogen atom, so the only possible values of J are going to be L plus 1 plus minus 1/2. Okay, it's very easy. L is equal 0, you end up with a single value. L is equal 1 or 2, 3, you end up with 2 possible values of J. That's great. So J basically follows the same kind of quantization that we've seen for L and S, and we call it spatial quantization, right? And it's not so different from L and S. Okay, so all these things we introduced so that we can describe the electronic levels of a hydrogen atom in the external magnetic field, or if we want to acknowledge the spin orbit coupling, right? And there's a special term that people use to describe these sort of fine structures of electronic spectra. They're called the term symbol. It's written here that acknowledges that there is a spin orbit coupling, and you have to know the values of the J. It also shows you the number of spin multiplicity, which for the hydrogen atom there's only like 1/2, right? So it's going to be 2. Okay, and this guy is going to show you the value of the total angular momentum, which for the hydrogen atom it could be 1s, 2p, etc. Right? So for the hydrogen atom it's quite simple, but we're going to carry this over to multi-electron atoms. So, you know, why don't we write it in a super duper general way? Here's a table that summarizes different J values for the hydrogen atom. So I say you don't need to memorize anything. Yeah, there are all these tables, you know, written for you. You can look at different values of J that results from different electronic states. The important thing for us is to be aware of, you know, spin orbit coupling and why we need this new angular momentum called J, and we need to know that that's because there is a spin orbit coupling. So S and L, they don't commute with the Hamiltonian, so you need to introduce some other guy that commutes with H, and then you can describe the joint sort of set of eigenfunctions with this new quantum number. Fine. We can get over this. Yeah, so from this table we can write down the possible values of J along with its different projections. Notice that as the J value goes up, right, so the number of possible projections, which is described by 2J plus 1, obviously grow. So if you're in a state that's L equal 3 and your J is equal 7.5, you have a whole bunch of possible projections of this J vector, right? You can think of it, you know, as J vector. It can be, you know, have this projection, that projection, that projection, that projection, that projection, that projection. Okay, so different different kinds of projections if we want some kind of pictorial representation, right, of the projections of the J on the z-axis. Okay, so we'll have some top hat quizzes when I come back on Friday. You can take a look at this example. For the most part, it's going to be very straightforward for the hydrogen atom, where you have a fixed value of S, so you can easily calculate J as L plus minus S, and you can calculate the multiplicity of J values. So having established this spin-orbit coupling and the importance of introducing the new angular momentum J, what does this do for us in terms of interpreting the atomic spectra, the electronic spectra of hydrogen atom and other atoms? And this allows us to explain the anomalous Zeeman effect, right? So the normal Zeeman effect was that you put it in an external magnetic field, and your energy levels were split, right? You had a 2p. These orbitals, and they would be split into 3 levels because of the external magnetic field interacting with the angular momentum L. Okay, so the anomalous Zeeman effect comes from the spin-orbit coupling, the fact that you now have this total angular momentum, and you can split lines even further. The key here is that to observe anomalous Zeeman effect, you don't want to have strong magnetic field. You can have a weak magnetic field, or you don't have to have external magnetic field, right? But if the magnetic field is too strong, then it's going to totally dominate over L and S, and so it's going to decouple the L from S. Okay, so if the magnetic field is too strong, it's going to completely separate the effect of L and S, so there will be no spin-orbit coupling, and you can throw the total angular momentum J into a trash bin and ignore the spin-orbit coupling. Okay, so this effect is pronounced only when you have a weak magnetic field or no magnetic field, and is known under the name of anomalous Zeeman effect. Okay, so basically, anomalous Zeeman effect is going to detect you all these different values of total angular momentum J, which is shown in this picture, right? So you have a state described by a term symbol here. It's written. You have a 3p 3 half, right? So basically, it's describing an electronic state where you have the J value is equal to 3 half, so it's going to give you 4 possible projections of the J value, right? And all these guys are going to be split because of the spin-orbit coupling. Okay, so here is what's happening to these term symbols as the spin-orbit coupling, how it's splitting the lines. So if you have a p3 3 half, it's going to split into 4 possible lines. Let me use a different color here, maybe orange. So you see that this guy is split into 4 possible values, right? And p1 half is split into 2, and you can have a whole bunch of transitions. So let's count them: 1, 2, 3, 4, 5, 6, 7, 8, 9. So you can have 10 lines. You expect to get 10 spectral lines instead of 2. Okay, so 2 lines if you don't acknowledge this sort of a spin-orbit coupling, and 10 lines if you acknowledge. And so these spectral lines, they're really fine because the spacing is very, very close. Right, so the spin-orbit coupling is a weak effect. That's why we call this a fine spectra. Okay, so if you want to really get down to these tiny closely spaced lines, you acknowledge for the spin-orbit coupling, and you do these accurate calculations, and then you can describe every single line in electronic spectra. And finally, right, to fully make sense of every single line that you observe in spectroscopy, you should also calculate the allowed transitions, okay? The transitions which corresponds to non-zero transition moment. And in other words, we need to establish the selection rule for the electronic transitions. So these are the rules. You see that you can only make transitions between states where the difference between total angular momentum is plus minus 1. And interestingly, this one that we're going to discuss quite a bit with multi-electron atoms and molecules, you see that the total spin must be conserved. Okay, so if you have some kind of a transition from, I'm jumping a little bit ahead, that correspond to the different values of the total spin, this will be forbidden, okay, by quantum mechanics. All right, so overall, this was quite a packed lecture where we discovered that all subatomic particles have spin, so we have to come to terms with it. There is no better way than just to acknowledge that the experiment shows different values of, of this spin, and therefore we have to build it into our quantum mechanics. And because spin has no classical analog, right, so we have to work back from the experiments and establish their eigenfunctions and eigenvalues. The good news was that as the spin operator works the same way that the angular momentum, and they're both source of the magnetism, and they basically differ by their by the nature of their eigenvalues. L can go from 0, 1 to 3. S is fixed at 1/2 for the electron. ML goes from -L to L. MS is simply bound to be either -1/2 plus 1/2, spin up, spin down. And the eigenfunctions for the angular momentum were the spherical harmonics, but for the spin, we just have these two guys, alpha, beta. They look very, very simple vectors, right? And we can write down their eigenvalues and eigenvalues of projections. And both of these guys are source of magnetism, right? We can connect it to corresponding magnetic moments, and these magnetic moments allow us to describe the full energy, the full Hamiltonian of systems that have electrons, multiple electrons, in the external magnetic field, in the absence of the external magnetic field, in the presence of weak magnetic field, and if we want to account for the fine structure of the spectra, we're going to introduce the spin-orbit coupling and introduce this J total angular momentum. Okay, guys, this is all I have. I may record another video, maybe talk about the homework problem. I want you guys to attempt and solve all the problems in this current homework, but I'll also be back on Friday, so I'll give you a hint on how to solve some of them, but to get most out of this current sort of chapter, you want to really work through the textbook, right? In addition to hear me talk about these concepts, you want to read and study independently, attempt the homework independently, and then when I'm back, we can all discuss and do top hat quizzes, and we'll have a lot of fun. Okay, guys, thank you so much for your patience. I look forward to engaging with you on Friday. Have a great weekend.